All right, okay. Hello everyone. Good afternoon. Isang maulan na hapon sa inyo or at least dito sa amin. Ay maulan sa office. But yeah, thank you for being here with us today. We hope that you're safe, even if tag-ulan na. All right, okay. Again, welcome to our National ICT Month celebration for this year. And yeah, it's something new this year. Kasi aside from the traditional ICT, we're now introducing quantum and particularly quantum computing. So, if you're here with us yesterday, welcome back. But if you're new, hello, we'd like to introduce ourselves. We are QCSP, or the Quantum Computing Society of the Philippines. And essentially, we build the Philippines quantum ecosystem. So, from advancing quantum technology like research or like projects, we also uh, foster collaboration. No, meron kami mga partners na mga universities, industries, businesses, and of course the government. And we want to nurture and enable the next generation of quantum professionals like you guys. We're so thankful. We're very thankful that you signed up for this special session for today. And also, aside from upskilling and capacity development, we also want to promote awareness for everyone na meron palang ganitong technology and it's something new and something na pwede maggamit on different use cases as well. So, aside from that, we are affiliated with the One Quantum Global Network. So, we are the local chapter, also known as One Quantum Philippines. We are also the representative of the Philippines to the Southeast Asian Consortium, and we are an endorsing and societal partner for IYQST 2025. Aside from that, as I mentioned earlier, we are in close partnership with DOST ASTI with their quantum AI and blockchain projects, and with DOST Fishered with our quantum PH program. So we have been doing this for a while now, pero this year it's very important since it's the International Year of Quantum Science and Technology. So we acknowledge that 2025 is around 100 years na when the formulations of quantum mechanics, quantum science has started. And even if we don't notice or we don't realize, but our understanding of quantum has really pushed the boundaries. And yeah, yung mga ginagamit nating technologies ngayon, semiconductors, our MRIs, and all of those, our cameras, branch out from our understanding of quantum mechanics. So for today, or yeah, before that, just a reminder, no, some of you might have asked questions yesterday are curious. We will give certificates for this session and news kahapon din, and that those will be sent to your emails. So, an evaluation form pala will be sent. Tapos, based rin sa Zoom attendance ninyo, we'll look into the Zoom attendance. And yeah, we can send your certificates within the week. All right. All right. So for today's session, so kahapon it's more on the industry or like the use cases of quantum, the new frontier of ICT, quantum computing. But today, it's a more on the hands-on, the applications, the quantum. So we have our second session, quantum computing at home, a demo using NVIDIA CUDA Quantum. All right. I haven't gotten, okay, my question, I haven't gotten any attendance and evaluation forms since yesterday. Yes, we will send them at once. Ayan, since magkasunod lang naman ng event. So we will send them tomorrow, and then you have until the rest of the week to answer it. And also, the recording will be shared to you as well. No, sa mga nag-register on the webinar, the recording will be sent to you. So if you're attending today's session but hindi naka-attend kahapon, don't worry. You will be able to watch that and get your certificate through that as well. All right, okay. So again, we have a special demo using NVIDIA CUDA Quantum. So we can use your NVIDIA GPU now to do quantum simulation. So our speaker for today is Sir Dylan Josh Lopez, the Director of Partnerships and Collaborations at QCSP. So he's also a research affiliate at De La Salle University, managing partner at Post Quantum Technologies Incorporated, technical panelist at BOSDP Shared, a member for DTI, Bureau of Standards for Quantum Technology Committee. He did his bachelor's in computer engineering, his master's in Taiwan on computer science and information engineering, and he's currently pursuing his PhD in electrical engineering again in Taiwan with his specialization in industrial quantum computing applications for the industry sector. Again, I'm giving now the floor to Sir Dylan. Let's give him a warm virtual round of applause. Woo.
Right. Hi. Hello, it's me again for those who attended yesterday's session. For those coming in this as their first session, hello. So, yeah, we're going to do a bit of weather checks with quantum again. So, in a few seconds. All right. So, a bit of background for today. So, we talked about, for those who came in yesterday, we talked about some basics of quantum computing. So, today we're going to talk more of an advanced field of quantum computing or niche field, which is quantum machine learning. So, for those who are doing artificial intelligence and analytics, this might be a lot interesting for you. So, let me just share my screen. All right. Okay. So we're gonna mainly do a demo on quantum hybrid quantum neural network. So we talked about something about that. So we're gonna debunk some of the things that is in this title in the next few slides. So what are quantum neural networks? What is a hybrid quantum neural networks, and what's quantum machine learning? So for those who don't know machine learning just yet, so I might skip that part, but just to give you a gist of what is machine learning in the next few slides. So without further ado, let's go into the several nitty-gritty of quantum machine learning and later on the demonstration. So for those who want to follow the demonstration later, we will have some links for that. So don't worry, you don't have to have a very special computer. You don't have to have a quantum computer to run the code later. But instead, you just running this in Google Colab. Let's proceed. So let's look at some of the topics here. Some review on classical AI. Let's review a bit on quantum computing as well. The emergence of the quantum AI and quantum machine learning, and some necessary quantum for quantum machine learning. We're going to talk about some theory in a very quick matter. Okay, and let's go ahead and discuss and work on quantum neural networks. So for those who were not here yesterday, this we're going to do just a very fast discussion on quantum computing. So quantum computing is a new type of computing that utilizes quantum mechanics to represent data, to perform logic, do operations, and do your algorithms. So quantum computing uses concepts of quantum mechanics and also utilizes quantum mechanical observations and resources so that we have advantages or improvement in algorithm development. So some of those concepts that are existing only in quantum computing are, idea of quantum bits or qubits, superposition, and entanglement. So this is not presented yesterday, but it's more of an overview on quantum computers. So we have quantum computing devices, more of what we call calculators that uses quantum power or quantum resources. So one of them is called a quantum annealer. Quantum annealers are very specific quantum calculators or quantum computing devices that focus on performing optimization problems. Analog quantum computers are more of a natural computer. So you have a problem, you have something that you want to simulate. For example, a problem in chemistry, a quantum chemistry problem, or let's say what we call a binary optimization problem. You can feed that into an analog quantum computer, and the analog quantum computer can solve that, using the natural course of physics and gives you an answer at the end. And we have a universal quantum computer or a digital quantum computer, wherein we have controls over what the quantum gates and quantum bits actually do inside the computer. So we have control units, we have several aspects of error correction. So that will have the fidelity of your gates. We have the integrity of what you're trying to read in and put in and read out on your computer. So a universal quantum computer is what we perceive to, perceive what an actual computer would be in the quantum sense. So it can do most of the bulk of work. So, for example, machine learning, cryptography, database searching, simulations. So more than just the optimization that the prior computers or prior quantum devices could do. Okay, so everything that we're going to discuss today would be running ideally on a universal quantum computer. So a bit of review again on the idea of information and operations in quantum computing. So in classical, in one point in time, it can only be zero and zero, either zero or one. It cannot be both. But in quantum computing, you can have a sense of reading the same thing at the same time. So the probability of observing zero and one can have, equal probabilities, or let's say 50%, 60% zero and 40% one, and so on and so forth. Okay. The memory in classical computing or any the regular computing that you know right now is 1:1. So if you have one bit, one memory of 1 bit memory is of course having only 1 bit. So if you have a quantum computer, you have 1 qubit would be equivalent to 2 classical bits. So if we have 2 classical bits, it becomes four quantum bits. It's equivalent to representing 4 classical bits. Okay, so there's a 2 raised to n efficiency on representing your quantum your classical bits in quantum. In operations, we have Boolean logic that's represented by gates, logical gates, and logic circuits, while in quantum computing, we are operating in the linear algebra scale. So we're all of your representations are not just numbers, but are matrices and vectors. So we use different kinds of operations for that. Okay, so I hope you're a bit refreshed, or you have at least the fundamental idea of how quantum computing works. Okay, so let's go ahead and try to mix this with the idea of artificial intelligence. Okay, so for those who stayed yesterday until the bonus part, we did a bit of a comparison of machine learning and quantum machine learning already, just a teaser. But let's go through that again. So the idea of machine learning, the very fundamental aspect is we take in any type of data and convert them into vectors. Okay. Now these could be in different way. It can be representing different things. So this could be a result of a classification problem, a forecasting problem, or it can be just generally embeddings of data. So you take in any data from the real world and spit that out as a representation. Okay, some call it tokens, some call them embeddings, but we just call them generally vector in the mathematical sense. And that vector, okay, is stored into some, well, storage, and those are in the real space. These are integers, there's negative numbers, there's floating points, all of them, okay? So if we want to add more representations, or you want to store more predictions of a machine learning algorithm, so we can, add more storage. But can we make this a bit more efficient? So yes, if the idea of quantum computing in terms of storage is representing 2 raised to n classical bits to quantum, then yes, that means we can change the idea, or rather modify the idea of machine learning in quantum machine learning to represent these vectors as not as real vectors, but now complex vectors. And if we store these, then it has better storing efficiency compared to representing them in classical. Now, also, machine learning, when we develop or spit out these vectors, then they're only in the real space. This is very important in the idea of feature extraction. So when we try to get the essence of anything, a data set, or any type of data you feed in a machine learning algorithm, we're trying to get its essence, the idea, the generalization, or some call it weights. So those weights are represented only in, well, the real space. Now, that's only one perspective or just one side of a coin of representing the data. Now, if we want to enrich that and try to see what else is representing that piece of information, then we might need to look at the imaginary space of that number or that representation, and that only can be done if you either specifically find the imaginary number that is another neural network dedicated for that, or a dedicated machine learning algorithm, then that increases again the complexity of your model. But instead of using a quantum algorithm or quantum machine learning, that's already innate. That's already given when you're trying to get the data or extract the features from a data set. Okay, so that's the idea of here, that your vector is now represented with something more. So that's cool. That means we have enriched ideas of your data set. Okay, so that will, in theory, and some applications as well, would help generalize better on a data set compared to just having the real space. Okay. So we did several review already of these literature in just the previous years, starting from 2021, and are, after analyzing over 150 plus journals in both Science Direct or Elsevier and IEEE, these are the application areas of quantum machine learning. So in terms of industry, networks and communications are the number one. Second would be health and remote sensing and energy, so on and so forth. They also apply it in economic and finance, road and transportation, industrial chemistry, and there are also applications in ecology. Now, if you're looking more of how this is applied as a technology, the number one application right now for quantum machine learning is computer vision. So there's also anomaly detection, time series forecasting, and also synthetic data generation, and so on and so forth. If you ask, are there applications already in Gen AI? Yes, there are. It's very few as of the moment. Natural language processing, very few, not reaching up to five in the past 5 years, but we are seeing a good development in the next few years in those aspects of AI. So, that sense, quantum machine learning as a research and later on as application is already starting to gain traction, and it's something that you might probably see in the next few years as part of your APIs. So if you are more keen in developing your own algorithms as machine or new novel machine learning algorithms, then you might need to look into one of the emerging topics such as quantum machine learning. So, or if you're waiting for it, it's better to know how it works right now. What's the advantage? Okay. So there are some hardware also that uses, of course, you need to use for quantum machine learning. So according to the literature, most of those applications that did declare their use of hardware, most of them are using GPUs and CPUs, more on the simulation base, not using explicitly yet the real quantum computers, starting from IBM Q, quantum annealers, Rigetti, and IonQ. Those are real quantum computers. So right now in the research, they're still focusing more on the use of simulations or regular computers. That means we can still use them as of the moment as quantum machine learning algorithms simulated on regular hardware that you have right now. Okay. So that motivation is out of the way. So let's try to build your theory or build the theory of QML in your knowledge base. Okay. So in summary, in these kinds of algorithms, then there are some hardware that are better than the other. Okay. So for example, quantum simulation that's trying to simulate, quantum circuits. So these are better in some hardware. So for example, in analog quantum computer is very good, but it could be a limited application in quantum annealers, digital quantum computers, or hybrid or your regular CPUs and GPUs. Okay. Now there are Oracle-based. This is, for example, the Shor's algorithm, algebraic-based. These would include, for example, Grover's algorithm, variational quantum circuits that would use also CPUs and GPUs, and there are very specific applications. Now, these would vary depending on what algorithm you're basing on, but QML in general would lie primarily on running on variational quantum circuits. And we'll get to that. Okay, so the main idea of how a quantum machine learning algorithm works, specifically quantum machine learning of quantum neural networks, is the idea of a rotation gate. Now, some gates would induce, for example, imagine that gates are just matrix operations done on a vector. So the very basic idea of a matrix operation is just linear transformation. So the idea is if you have a vector pointing up something like here or pointing into the left, so it can only do linear operations. It could be rotations, it could be expansions, it could be shearing, and all of those. It could be flipping as well. So if you have something going up and then you suddenly flip them downwards, that's actually what we call the X gate, which tries to flip the operation or to negate the operation. So you're trying to flip it across its axis. Okay. So there is also a very special operation in quantum mechanics or quantum machine learning or quantum computing is the rotation gate. So given some sort of parameter, okay, so for example here phi, and you have this matrix right here, so you can dictate how the rotation of a certain vector would happen, similar to what you're seeing in this animation here. So given the input of our angle, it can rotate according to some axis, in this case, the y-axis of your qubit. So we can try to induce this kind of operation so we can find or try to fine tune the vector's orientation. Okay. So there's also the concept of variational quantum algorithms. So in the very basic sense, a VQA or variational quantum algorithm is a set of computers, a set of programs wherein you have a quantum program that runs an algorithm, probably a quantum circuit or a quantum algorithm, and the output of that will be validated in a regular computer. So imagine that it is trying to just spit out a value and you're trying to evaluate that value in an external program which is existing on a classical computer or regular computer. So one example of this is computing for a gradient or trying to minimize an operation, similar to your neural network, if you're very familiar with that. So say, for example, we have a quantum neural network or just generally a black box model, and you want to minimize the parameters or minimize the error of your model. So the error is being computed in your classical computer, but you feed back all of the parameters back to the quantum algorithm. So similar to the idea of how to optimize a neural network. So here we are. Let's talk about quantum neural networks. So the generic idea of a quantum neural network architecture are as follows. Okay, so in your circuit, so it always starts with a quantum encoder. So from your regular data, you have a data set. So that data set will be now fed to a quantum encoder so that the data will be turned into the quantum states because you cannot just feed randomly your data over there. Okay, so it has to be encoded onto the qubit, okay, using various methods. So you can represent your qubits as here as your different how many batch sizes that you want to work in, but sometimes we determine the number of qubits depending on what's the output vector size. Okay, so after that we can now add quantum neural network layers. So we'll discuss how these neural network layers work and form in the next few slides. Okay? So we can stack them. So imagine that you're just adding several neural network layers that becomes a DNN or deep quantum neural network. And at the end, we observe that using measurement gates. That's the Z and the meter there. So that's a measurement operation that is converting quantum data back to classical data. So because we want to analyze it probably in a separate program or an optimizer. Okay. So in this sense, so if you have, let's try to zoom in into how quantum neural network is formalized. So in this case, you have your quantum encoders, you feed in your classical data, your data set, then you also feed in your weights. So these weights are what you're trying to learn. How are these represented? And these weights are the angles of the rotation gate. So imagine that you are trying to find out what is the right orientation of the qubits representing this idea, okay, of your data set. Okay, so you're trying to adjust the knobs of all of your qubits, both in X, Y, and Z, so that which direction points to the main idea of a certain data set. Okay, so that's another way to imagine that. Compared to the regular neural network, instead of, in this case, the regular neural network are just knobs of going up and down of all of your weights because it's only in the real space. Okay, so you're just adjusting all of those weights up and down, and which of those combinations would best represent all of your output vector. Okay, the idea of learning this classification vector or learning the idea of this forecasting vector. Okay. Sorry. Now, those are what we call the parametric unitaries. Now we induce entanglement in all of these here. Okay, so entanglement is the relationship of all of your data. So there's inherent correlations. So that we induce them in this kind of circuit, and of course, then we measure them to become your classical data again. Okay. So we're going to get some parts here. So one, and this main idea is how do we set number of qubits, okay, and or how do we set the number of gates. So the number of qubits, it depends on the number of your output vector, okay. So n here, there, n represents the number of qubits, while m is the shape of your matrix, okay. So you can have different sizes of, or actually orientations and configurations of your quantum neural networks depending on the size of your matrix, your matrix and your vector n and your matrix m. Okay. So let's try to break down how each of these work. What's the concept behind them? So the encoding layer you tries to accept classical data and which we encode them as and we spit them out as quantum data. So in this case, so we are trying to encode them either as the amplitudes or the phase of a qubit. So it's already, there's inherent rotations already. Then after that, we now try to learn which the rotations in the x and x, y, z, or any specific axes of your qubits, so that it would best represent that. So imagine this like really just turning the knobs of all of your qubits that represents the learning of or the essence of a certain topic or your data set. Then we apply entanglement to that having their correlations. Imagine this, that's all of those lines of your neurons going to one another, creating a bipartite graph. So that's the similar idea here. So instead of putting them those relationships as just lines, these are represented as real quantum observations, which are entanglements. Then we try to measure them so that they become classical data. Okay. Then it's also important in neural networks to compute for the gradient because that's the improvement. So once we compute the gradient of your neural network, we can now perform backpropagation. That's something that we can compute together with an external optimizer, for example, Adam, Adagrad, SGD. So you can try to get that and feed it back to the quantum neural network to adjust all of those weights, all of those rotations. Okay. So I'm going to skip discussing this, but the general idea is this is how you compute the gradient of a circuit. So what happens, just you shift all of the weights forward by zero point 0.5, or let's say 90 degrees, then shift them back to 90 degrees. So you're rotating them all forward and all backward, and you get their difference. That's the gradient. So that's the main idea. Okay, we're not going to go through the mathematics of this, but that's how you would relay the gradient computation to the gradient optimizer. Okay. So what's now the idea if we try to make a hybrid quantum neural network? So why do we need to do this? Right now, we're in what we call a noisy intermediate scale quantum computing era. That means the number of qubits that we have right now are still improving in terms of quality, because the slightest change in temperature can alter the information, and we don't want that. So we take into consider that, and also the number of qubits, and not are currently not enough to represent fault tolerance. That means, again, the noises and the vibrations. So what do we do in the NISQ era is we also look at the power of regular computing, high performance computers that works with quantum computers so that we can get the job done. Okay, so this is something that we do as a common practice as well in quantum neural networks. Hence, we create a hybrid quantum neural network. So the idea of implementation of these HQNNs, or hybrid quantum neural networks, is that you have your input vector, you have your classical layer, and after that you can apply a quantum layer. So it can be a regular quantum neural network, a quantum convolutional neural network, or even a quantum LSTM. So those algorithms also exist already, and these would include all of the operations that we have discussed prior. So one example is that, for example, you have your MNIST data set, then you have your regular convolutional neural networks, for example, DenseNet right here. And after that, you can actually apply a quantum neural network to enhance your classical network or backbone. So that would enhance or try to find out better extractions from your input data set. So this actually could bring about some improvement. Okay. One of the things that we also did with this is our recent research just earlier this year, or actually just earlier this year and finished just recently last year, is how do we do forecasting, weather forecasting, just in this case, sunlight forecasting, using a modified 2D neural network. Okay, so we can improve the state of a neural network by just adding as well a quantum neural network. Okay, so there are other ways as well to do this. There's also what we call a quantum encoder architecture, wherein we do the quantum layer first before the classical layer, or it could be the dressed quantum. That means you can sandwich the quantum layer between classical layers. That's also applicable if there is a shortage in the number of qubits. Sometimes the number of output vector, or the size of your output vector, could not accommodate, or rather the number of qubits could not accommodate the requirement of the size of your output vectors. So you might not put your quantum neural network there, or nor the size of the input. So you put somewhere in the middle. So this could be somewhat like an autoencoder architecture. So it goes smaller at one point, then suddenly expands on the other. So that's one architecture similar to that. Okay. So one of our examples where we did a quantum encoder circuit using quantum convolution networks is in this example. This is actually satellite image prediction. So you're trying to try to predict the frames of a video, but in this case we have satellite images, and we try to improve that by using quantum circuits as a data augmentation algorithm, so that we can try to find out better representations of that before we feed that into a neural network. So this is something that we did earlier this year as well. Okay. So moving towards something more technical in what we're running. So we can try to do this with our own hardware. So if you are working on your regular GPUs, this is something that you can actually do. So if you have, for example, 3060 GPU, RTX 3060, you can actually simulate quantum algorithms up to 32 qubits. and that's amazing. But if not, you can just use something online, just like Google Colab. Okay, so for example here, so if you know already a bit of neural networks, then you might have heard of CUDA. So CUDA is hardware acceleration software by NVIDIA, so that enables your GPUs to become more efficient in uh, computing matrices. Okay, and these kinds of algorithms or these kinds of acceleration could help speed up or even better apply quantum algorithms or any specific operations with your computer. Oh, so I think this has been messed up. But anyway, so again, CUDA again is your GPU acceleration. So CUDA has a lot of sub-libraries or packages that could help you improve with your very specific applications. Okay. So for example, you can use it for, well, rendering images. You can also use it for linear algebra. You can use it for specifically deep neural networks. So you can use those kinds of applications. So one of them is CUDNN. This is CUDA for deep neural networks. So it enhances the performance of your GPUs for its applicability in neural networks. So if you already done custom neural networks before or just run it on your own, you might have heard of CUDNN somewhere. So that's one way. It's accelerating performance for neural network training and validation. Training, validation, evaluation, and also some parts of inferencing. And there's also 𝐾𝐢𝐠𝐢𝐭𝐚𝐥. So 𝐾𝐢𝐠𝐢𝐿𝐿, similar to CUDNN, is an acceleration library that allows your computers to perform a certain task, and this sends quantum algorithms. So for example, here we have two-state vector. It helps your memory or GPUs and GPU memory to allocate better in terms of quantum algorithms. So how do we do all of your operations, quantum algorithm operations powered by NVIDIA GPUs? There's also q-TensorNet, so representing all of your circuits as tensors would help into how do we represent this in the larger scale. And there's also something that you can use in Python. So there's cuQuantum Python where you can use all of these, program this in Python. But right now, we also have what we call a CUDA Quantum Platform. So CUDA Quantum Platform was released in 2020, in the mid of 2023, wherein you can now use your CUDA stack in creating a pipeline or your workflows in hybrid quantum applications. So you can meld this with your pipelines using GPUs as well as real quantum computers and also simulated quantum computers. So if you want to design something that first prototype is prototyped in a GPU, you can use CUDA Quantum. But then if you want to migrate to a real quantum computer, you can just change one part of the settings, and but your code does not change. So it's very useful, especially if you want to lay out a pipeline or lay out your quantum machine learning workflow using CUDA. So here, if you want to dwell in the details, so CUDA Quantum allocates all of your memory here for several parts of your equation. So your equation could be represented by several what we call here sub-problems, and this could be partitioned into different resources, so it could be different GPUs. So if you have a distributed computing setup in your workplace, or if that's something that you can avail, then this is something that CUDA Quantum can orchestrate for you. So I think we can now go to the demo. So we can have a bit of 5 minutes. Let's take this time to breathe, try to ingest everything so far, and to try to access our try to access the link right here. So yeah, aside from this, I would be sharing the actual link for you guys. Let me just wait. Just get my um, where's my where is it? Let me just stop sharing my screen. I'll just send you all of the links for the demo. Ah, here it is. So I have two links. One is more of a tutorial, so I will not demo it for now, but if you want to learn more about uh, yeah, if you want try to learn more about all of these, okay, and here's one. So you can try to learn quantum neural networks here. So there was a question earlier about the forms. I believe that will be sent via your email in the next few days. So yeah, please watch out for that. So I'm not handling the current forms right now. So sorry for that. Um, but I'll be sending the actual link for the hybrid quantum neural networks, which we will be uh, demoing. So the second link right here is what we're going to use for the demo. So for the one before, it's actually more of a tutorial on what are quantum neural networks and the very basic aspect. So let's start at 550. Just I'll allow you first to access the links for now and make sure to tick on your GPU access. Okay, so for those who already know, for later, I'll just show you how that is. Okay. So also for those who want to take a break, that's cool. All right. So let's continue. So for those who have accessed it. So, all right. So in this notebook, I'm just going to demo on how hybrid quantum neural networks work and how do we form that. But I'm not going to dwell too much on the technical details of how each line would work. That will call for a different tutorial. But yeah, if you have interest in that, you can send us an email that we can if you want to have that specific tutorial for hybrid quantum neural networks. So, all right, so we discussed everything so far that you need for the theory of hybrid quantum neural networks. So let's go here. So here, I'm just gonna install your CUDA-Q. Oh, before that. So for those who did not check yet, please make sure that you're connected to your T4 or any available GPUs that you have. So if you are on Google Colab Plus, then that's or Pro Plus that you that's actually very cool. Then you can access a bit better. But for those who doesn't, so you can access your T4s. Okay. Then you can run this line and you'll be installing your CUDA-Q the version 9.1. And this would allow you to have your CUDA. So after that, you can run, try to restart the session so that you don't have to run it later again. Then I'll just go through some parts. So here we're already importing, okay? And we're just importing your spins. Spins are, more of how do we set or, manipulate the property of a qubit here. Then we're going to have all of your machine learning libraries here. In this case, we're using PyTorch. And of course, we'll have your train test split as usual. We're just going to set the seeds here for reproducibility. Okay. Then here you can actually select different hardware for your runtime. So in this case, you can check your device to become a CPU, or for here, your CUDA-Q can be set. Imagine that this would be setting which device should you be running the quantum algorithms on. So you set device here as your NVIDIA. Then for your for your regular neural networks, you need to set your CUDA. That needs your first GPU. We have our libraries there. Then for dataset preparation, so this is very basic. I'm not going to go much into detail here. This is more of a classical neural network, classical machine learning task. So I'll just skip this part. So that also includes already your train test split. Then all of your parameters here. So we're just scoping the problem in this case. So we're gonna use more of a binary classification. We're gonna do a 5 and 6 classifier. Okay. Our threshold will be just 0.5. Then our epochs, training epochs will become so instead of 100, we're gonna do this by 5 for the moment because we don't want to wait for a long time. This would probably take 30 minutes if we use 1000 epoch. So we just use or 5 or 3 just for the sake of running this algorithm. So here we only need 1 qubit because this is a binary classification problem. So since the output vector is just 1, then we only need 1 qubit. So if we have like for the whole MNIST data set, then you need 10 qubits, okay? And that will change a lot of things in the whole algorithm. So if you want to do that, please do that on your own free time. That will be a very good practice. Uh, then we'll have your Hamiltonian measurement here. That's just measurement, Z measurements. Don't stress yourself too much on that yet. Okay. Then we'll have the parameter shift as 90 degrees for shifts. So that's for the gradient computation later. Then let's try to plot some of the data that we have. After it's there, we have 5 and 6 classifier. Then we can now prepare your QNN. So remember that we have four main parts. So once the quantum encoder, we have your parametric unitaries, your quantum correlations, and the measurement layers. Okay. So we do that by creating a custom function in PyTorch. So this is something that can be done in TensorFlow, but it's a bit hard for those who have experience in creating your own neural network layers. So it would be a bit taxing in terms of coding this by manually coding this. But in PyTorch is very straightforward in most sense. So it's for the research aspect, this is very straightforward. Okay. So for example, your quantum function here, this would be your customized layer, neural network layer in your PyTorch. Okay. So here we can have your qubits. Okay. We set the number of qubits. Then we have your rotation gates. So these are parametric quantum circuits. Okay. So there's actually a question here. It's actually for the last class that used this code. So we did have a question on how this why does the NVIDIA sample code does not have a quantum encoder. Um, I think if you can answer this, and I'll be happy to discuss this with you. But I'll also leave this question to you guys on why did they not have a quantum encoder in this sense. It's actually more of a technical aspect rather than a theoretical aspect. So you can check that out. But in this case, we're just going to create a very basic a very basic um, quantum neural network. So here we're just going to have directly having it in the parametric circuit. Then after that, you're just going to have measurements. No need for quantum correlations because you only have 1 qubit. So you only need to have correlations, or you need to have your entanglements if you have 2 or more. So in 1 qubit, you don't have to do any type of entanglement. Okay, so here is just running the quantum circuits. It's more of just observing the values. Okay, so we're just gonna run this. So that's this serves like a feed forward operation. Okay, then encapsulating that, we have that in actual feed forward function. In this case, so we have your quantum circuit running here. Then we have need to customize your backward propagation function as well. So this now implements the finite difference, or what we call as the parameter shift rule. So we can run that here. So that is a customized back propagation. Then we now encapsulate all of those in an actual neural network layer. So we're going to inherit that from your neural network module from PyTorch. So upon initialization, just creating the circuit, then we'll have your feed forward function here. Okay, that's it. Then let's try to create the pipeline. So in the hybrid quantum neural network is how you do it in PyTorch. So you identify all of your neural network, classical and quantum neural networks here. So say, for example, in this case, our first fully connected layer is a linear is a ANN, which has a 28 by 28 by 25 by 256. Then we have a 256 by 128. Then we have a dropout layer. Then we have all of your other ANNs right here, fully connected layers. Then lastly, we can declare your quantum neural network layer here. Okay. So what's important here is you have your output set to 1. Okay. And we're good to go. Then we can now arrange all of this in the actual neural network format that we have. So we have all of the sequential parts of your fully connected layer. So we do layer one, layer two, do a drop out, layer three, four, and five, which is layer five is here, this 32 by 2, which is actually, imagine it like a very narrowing funnel of neural networks. Then finally, you can now go to your quantum neural networks. So finally, this one would employ a sigmoid function as an activation function, again, because we're doing a binary classification. Okay, so that's it. That's how you would do your classification or organize your HUNN architecture. In this case, it uses the output layer as your quantum layer. Cool. Let's run that. And let's just define the accuracy score function. Then let's have it here in our model. So it's just the regular things. So this one uses ADA delta. You can change this to ADAM if you want, SGD or RMS prop. We're just going to send it to the GPU. Then we're going to train the model here. So we do a zero grad, start with your Y data, then you have your computation of the loss function after you do the feed forward optimization, or feed rather just the feed forward. Then you do a backward propagation here. Then we just report all of your training accuracy and cost. Then we'll do the validation here. So is it running already? No, I didn't hit run yet. Anyway, I'll get a start. I was surprised. So there, it's now running. We're just running on 3 epochs. So we're going to expect it's not really that good. But if you want to make it a lot pretty, oh, there's no render feedback. Okay, this was an error. So let me just go back here. Yes, because there was an error because the data that we're accessing is still in the GPU. So training cost. We can stop this for a while. Right, but anyway, so this would how it look like because we don't have a very finished process. So here we can see your test still lower, I mean higher than your training, but we haven't seen any optimization yet. Okay, this is on your costs. Your accuracy was not yet computed because let's see. Yes, it's propagated from here. It should be going back to your CPU. Anyway, yeah. For those who, yeah, I'll just fix this once you check the updates. So I'll be sending this later. Anyway, that's I mean, I don't want to do live debugging here. But yeah, at least we know what the problem propagates. But yeah, this would work. Actually, the training does work. It's just, the visualization does not right now. But yeah, you can increase the number of epochs here to see the difference. So you can try it on your own time because we don't want you to spend too much time on training during this talk. Right. So allow me to go back to the slides. We do have some, just a very few slides left. Okay. Oops, sorry, that was the slide. So the last one is on the future directions. So there are future directions that we are expecting with quantum machine learning. Of course, we now have machine learning operations. We also have quantum machine learning operations, but it's better to note which hardware is good or applicable for these quantum machine learning operations. So for example, data retrieval does not require a quantum computing device, but data analysis could. Encoding has quantum computing, but for others would not require. For example, hyperparameter optimization would not have your quantum computing unless we see developments of that. For example, in circuit compilation and sampling and measurement, those are still done on quantum computing devices. Model quantization right now, we don't have any developments yet on quantum computing devices. So this is solely on CPUs and GPUs. Okay. So if you want to know more, we are publishing a paper in the next few months. So please watch out for that. So I'll be posting them both on LinkedIn and on Facebook. Cool. So I guess that's it. So if you have any questions, I'd love to entertain them. For other logistic questions, such as the certificates and attendance forms, um, Jabez will be reaching out to you in the next few days, or most likely tomorrow or tonight, for your certificates as well. So please wait for that. Okay. So for technical questions, I'd love to answer them. So we're now open for Q&A. Especially for those who are more on the ML engineering side. Okay. So just send your questions at the chat box and that'll be cool. So for advanced questions, no, nobody has done too much QML in the Philippines yet. All right, so if you want to start with QML, you either start with the Q or the ML. So you need to go one way or the other. So if you want to start or you are in the AI industry already, try to learn more on the ML side. Then you'll have an easier time learning the quantum. Now, if you're in the quantum side, you're happen to be a physicist. Need to learn about quantum computing first, then machine learning, or together. Okay. So if you want to, for example, learn this from the ML perspective, to review your linear algebra, review some quantum computing packages such as PennyLane. There's also Qiskit, but NVIDIA CUDA Quantum has their own package, so that would be enough as well. And that would now be easy to integrate. So it's a bit hard if you don't know how neural networks work. So better to work from there before you go to quantum. Okay. So how does the noise in quantum circuit really affect the accuracy of the model? And how do we mitigate? So it depends on the device that you're working on. So one way to do that is to really prototype your model in the ideal state, which is just in regular CPUs and GPUs. That will give you the ideal training that you have or expected training. However, if you want to induce noise, NVIDIA CUDA Quantum and other platforms can help simulate noise in a quantum computer. Now, that would affect greatly on your accuracy because there are bit flips. That means it's not just error from the program that you're trying to capture, but you might be capturing the noise of the quantum computer that is affecting the error of your model as well. So that's going to be catastrophic if your model is learning from the error of a quantum computer. That means you're skewing away from learning from the data set. Okay, so that's really scary. Mitigating this is really trying to understand the behavior of the noise before you feed it to the actual quantum computer. That's why we try to simulate it first. Okay, so that's one. So the next would then be is to select a quantum computer that would have a good that would meet your tolerance in terms of noise. So, for example, if you're using a superconducting computer, that would be good enough for you because each of those quantum computers has their own error correction and um, error mitigation routines. So it's not the same for all quantum computers and or all platforms. So you might need to benchmark that for yourself first. Okay. So next question from George. Are there currently applications in QML fields such as healthcare, medicine, and pharmaceuticals? I'll go in the reverse order because there are a lot of applications in pharmaceuticals because this would be used for finding better matches of uh, existing medicine with existing illnesses. So machine learning is used there primarily. So you can just improve that with quantum machine learning. Then there is a very big abundance of applications in imaging. So those application that has MRIs, CT scans, X-rays that uses computer vision has a lot of applications with quantum computing as well. So that will help you a lot in the research. So I would update you if once our paper has been published. It's actually a review of all of the QML applications, and the bulk of that discussion is in healthcare. So we are going to showcase some of those applications in not just in those aspects. We have a lot of hierarchy. So there are applications in oncology, there are applications in medical technology, imaging, of course. There is also in medical administration, there are in that aspect, and so on and so forth, and also pharmaceuticals. So we have a lengthy discussion on how QML is applied in the healthcare industry. Right, cool. Vincent, you're a chemist upscaling and leveling into computational chemistry. Cool. What's the simplest roadmap can you suggest on your trajectory becoming a quantum computational chemist? So we're gonna skew away from this discussion today. Um, if you're in the computational chemistry industry, you are very near already in the quantum computing industry. One is because you already have not, assumably you already have knowledge in quantum chemistry. So knowing about the Hamiltonians is actually a very good advantage for anyone entering the field. I have not mentioned any Hamiltonians in the past two talks. This is the first time. So if you know what I am talking about in terms of the Hamiltonian, that's actually very advantageous because once you have the Hamiltonian of your quantum, let's say your problem in quantum chemistry, you just directly feed that into the quantum algorithm, and the quantum algorithm will solve that for you. So finding the lowest state of your quantum chemistry problem. So one, probably in your domain, brush up your quantum chemistry because that's the interface between chemistry and quantum computing. The language of quantum mechanics would be very helpful. Um, Two is going back to the idea of quantum computing. You need to know a bit how the quantum computers work. The one I mentioned about Hamiltonians is not exactly the digital quantum computer, but either quantum annealers or analog quantum computers. So since these are the natural state of quantum mechanics, you can just really simulate it directly. So understanding quantum mechanics in that sense is very advantageous and how the quantum computer works. But if you want to work that in a digital quantum computer, then you might need to brush up with your linear algebra and your coding skills. So it's great that you're doing this in the classical sense already in computational chemistry, but then if you want to do quantum computing, you need to revisit your quantum chemistry and of course programming. So yeah. From Mark, for computer vision application, does increasing the qubit number for multi-classification advantageous? It's not a matter of advantage, it's a matter of requirement. So if this is assuming that you're asking about the quantum neural network at the end, okay? So for that aspect, then it is a requirement. Okay, that means whatever classification number that you have should be the number of qubits. There's not you cannot have less, you cannot have more because that's the exact qubit requirement. However, if you're talking about the input, quantum neural networks in the input, again, that depends on the size of your input. You cannot have more or less because that's the requirement of size. So the only way now you can look at increasing the number of qubits is uh, the third option, which is dressed quantum computing. Now, that is also it actually depends. We don't actually know unless you have tried to simulate this already just in a regular computer. So, does a three neuron problem or three neural network will prove advantage in that kind of setup? And if you increase that size, does it improve as well? If the answer is yes, then most probably the qubit increase would also improve. So I'll just give you a bit of a background on how do we design this uh, in the most realistic sense. So it's not highly computational. It's actually in the experimental way. We design first the regular neural network, the regular classical neural networks, and we just identify which part or select the neural network we want to upgrade or change into a quantum sense. So normally we optimize the neural network based on its classical settings. So we try to do hyperparameter parameter optimization on that and identify which is the number of neurons that are advantageous or ideal for this problem, given the data set and given all of the targets. So, for example, if you this part is what we select for a quantum neural network, then we just select the number of neurons there as the number of qubits. given the constraint of having the qubit size. I mean qubit availability of a quantum computer. So in summary, the answer to your question is it depends. So yeah. Okay. So I hope you can try all of this in your own device. So if you have your own RTX 3060 at your home or office, you can readily just download the code and run it on your computer. You just need to check some CUDA installations. That's the hardest part in any type of AI pipeline, not just in quantum. It's the CUDA installation. So if you have already a setup there, that's going to be cool. Okay. Right. Any other questions, clarifications, or valid reactions towards quantum machine learning? Right. Again, there's no other implementations yet on quantum machine learning in the Philippines. So if you want to try that, please do. I would love to help you to develop these algorithms for our country on your work, or even just a regular research on your undergraduate. So just actually, please try, these new technologies for your applications. Okay. Right. So if we don't have any questions, oh, okay, good. One more question. What are the current limitations we have in performing efficient applications in QML for IoT devices? Number one is the availability of all of this in terms of the pipeline. Okay. So currently we are restricted with all of these QMLs with what do you call this? Having just local implementation. They're all for training and evaluation. We haven't seen their application. Well, inference, yes, but we can't see their application in the edge. Okay. So if we're looking at the implementation of IoT systems with AI on the edge, then that's going to be the main bottleneck because we don't have um, edge devices that could handle quantum machine learning algorithms yet. However, if we want to see this as a centralized, like an API kind of thing, then it's just the same implementation pipeline, similar to your regular IoT with AI. Okay. But in that sense, if you're looking at the centralized AI, then the problem is data. So since IoT data is very vast and very, it hits all of the V's in the five V's of big data. It's more of how do we process all of this. So I'll give you one hint on how this is going to be vastly complex. Even though the implementation of the training and inference is quite optimal for quantum optimization, or rather during the quantum machine learning optimization, the encoding of the data might take a lot of the time because the time to encode the data is different from time to optimize from the data. So you might face problems, a technical difficulty in having all of your classical data be converted to quantum data in a pipeline. So that's probably an expected problem with IoT-based ML, given the uh, veracity and variety of your data. Okay. How do we contact you? You can search me via LinkedIn. My name is just the same. I think this is my name, or this is my name. You can check me on LinkedIn, or you can send a message via the Facebook group of Quantum, not Facebook group, Facebook page of Quantum Computing Society, requesting my connection, and that will be also fine. And we can set up a meeting if you want for these kinds of things. So, but if you want to send an email, here's my email. Oh yeah, I saw you yesterday. Sorry, I'm just really busy these days, so I'll be replying probably on Thursday because I have a flight in the next few days. So sorry for that. So this is my email for those who want to have more of a professional discussion via email or connect you to other of your friends that did not attend this webinar. Then I'll gladly to be glad to contact you or talk to you via email. Right. So if we don't have any more questions, you can send the questions via email or LinkedIn. Just expect some delays. It's quite just like Job has mentioned. It's the International Year of Quantum. We do have a lot of events lately. So, and we're very few manned right now. So, we have a lot of things on our plate. So please be patient in our replies, but we'll get you to that. I will get to your questions. All right. So if nothing else, again, please wait for via your email all of your certificates and your evaluation for the past two seminars or webinars. But if not, please send us a message on the Facebook page or send me an email directly, and I'll be forwarding that to our operations team. So if nothing else, guys, thank you and have a great evening.